Welcome to Hacienda del Resny. This is my house. Okay, so I've here a toy. This toy, I hope you can see it pretty well. I'll bring it a little closer to the camera. Nope, gotta go backwards right there. I assure you the red rectangle is not real. That's, you guys know what that is. So this toy right here looks like this. And so that's the question. What is the volume? What is the volume of this object, not counting the little magnetic stoppers in the bottom, which I like to put on the refrigerator? What is the volume of essentially the liquid inside there? And then again, technically, it's about 1/4 and 3/4, two different kinds of liquids in there. Well, just not worry about that. They can figure that out later. I just want to find the volume of this thing. And the problem, of course, is what's the formula? This is a curve. It's a parabola, right? And this end is like this. So how would I figure out the volume of this toy? Okay, so the way I'm going to ration this out, I'm going to say, look, I know that I can still do area times length. I know I can do that. The problem is that if I were to picture this, if I were to note, each one of the rectangles going around the outside, destroying the kid's toy. There's a certain 3-year-old who's going to be angry at me. And I can make the toy disappear. He has no attention span. Okay, so I drew. Oh, can't see that at all because the backlighting is horrible. Who did the backlighting? Oh man, I can't see. Okay, there you go. Okay, so I drew a rectangle. So this is a rectangle, right? If you pictured it end on, there's a rectangle there. There's a rectangle there. And so as I'm looking at the shape, right? Be nice if I did some better camera work here. If I look at the shape, head in front of the light. Okay, so if I did the shape, okay, there'd be a rectangle as I'm walking through this rectangle. So if I imagine myself walking through this toy, I would be walking through this rectangle. Everywhere I stopped, my base, my heights, and my coming across the roof would be the same, right? So if I looked at this, my roof, you can barely see that. Okay, I can move my head the wrong direction. Okay, so the height would always be straight across, right? Now, the problem is, although this doesn't change, this dimension on the side is going to change every time, right? As I walk this way, it'd be shorter. As I walk the other way, it would be taller, and then get shorter again. Okay, so finding the volume can't be just length times width times height. Well, it is, but I'm going to have to deal with the fact it's changing. Does that make sense? Okay, so what I'm going to do now is I'm going to now switch off the camera. Okay, switch off the camera, and then we're going to talk about this very shape here. All right, so let me pause this. Boop. Actually, I don't need to pause it. Just get it out of the way. All right, so now I take a look at my funny shape, and I've taken some measurements of it just to, and these are legit measurements. If it was a rational world, I'd pick numbers that work better. But I'm just going to go ahead and do the one we had in front of us, which is technically, so I found that this is what the shape looks like from the edge. I know when I walk through it, each of the little areas are going to be rectangles. Some will be taller, some will be shorter. And that as I go from front to back, I'm walking this way. So I'm going to declare that this direction here is dx from the earlier thing. I'm going to call this point here 0, 0 to make my life better. And I'm going to say this is that curvy bump on the front. Now, I'm going to note on that I measured this. This is 3 centimeters. Okay, math class, I don't have to worry what this is. Unfortunately, this is the dimension that's changing, right? As I go slicing my way through that, it's getting higher and higher. So how would I find the volume of this thing? Well, I find the volume of this thing simply by going, all right, area, in area format. Area is going to equal the rectangles, right? So that's just going to be, pause a moment. Usually I let the class figure this out. It's going to take a while, but I'm going to go ahead and go, I hope that makes sense. Okay, if not, think about it till it does, because otherwise this is not going to make much sense. So now I'm going to walk through the rectangles from left to right along this axis. As I do that, I'm going to integrate each one of my areas. I'm going to multiply each one of my areas, and I'm going to make each one skinnier and skinnier. Whoops, 3y. I'm going to make each one skinnier and skinnier until I get to the end line. Now, I measured this distance from here to here. What did I get? Let's see, trying to be, 10. But I'm going to, ooh, that's a problem. Okay, so I did not want to make this 0.0. I'm going to make this 0.00 so it's symmetric and makes my math easier. So I do apologize, okay, for those of you actually following along. That's 0, 0. So this is 5 centimeters and this is negative 5 centimeters, okay? So I'm going to integrate from negative 5 to 5. Now, of course, the problem is this says dx. So I didn't do my job correctly here. I need an area formula that is in terms of x, so I can walk in the x direction, know how high my roof is as I'm multiplying along. As I multiply each of my little chunky areas, I need to know what each of my heights are with respect to x. So now I go back over this formula, and I have to figure out what the height of this is in terms of, I need a y equals question mark. Okay? So, in playing with this, I recognize it's a parabola. I recognize it's 10 centimeters long, so I made this negative 5, made this 5. I made this height here. I checked it out. It's a whopping 2.5 centimeters. Yep, that's real. Did make it nice for us. And so then it's curving like this and going down like this. Hopefully you all know how to model this, but I'll quickly go over it. This is actually not a really testable idea, but you should be able to do this, right? So it's centered at 0, 0. I can get away. So it's centered at 0. I can get away with this particular model, x squared plus y-intercept. When I plug in 0, that's going to be 2.5, so I put a 2.5 there. I recognize this has to be negative because otherwise nothing's going to make any sense at all. I would then say y has to be equal to, at this point, 5. So I'd go, well, then when x is 5, y has to be 0. So I put a 0 in here. I'm going to go negative a. Whoops, come on. Pen's not working. Doesn't want to work. 5 squared plus 2.5. I recognize this is going to be negative 2.5 equals negative 25a. Therefore, has to be 1, which is remarkably nice for an actual problem. So therefore, my equation for y is going to be y equals x squared plus 2.5. So that is my height equation for every value of x. So I go back to my area land, and my area form is actually going to be 3 times negative 1/10, because that's what y is in terms of x, plus 2.5. Running out of space, I do apologize. So that my area formula is negative 3/10 x squared plus 7.5. Now it's my area. I'm going to integrate it because now I can. Negative 5 to 5, negative 3/10 x squared plus 7 times x. Sorry, 7.5, not yet times x, but will be in a second, dx. All right, raises power by 1, divide by the power I get, and I get negative 1/10 x to the third plus 7.5x from negative 5 to 5. I plunk in my 5 there. I get 125, so that becomes negative 125 tenths plus 77.5 times 5 is going to give me a 5. Carry the 2, 37.5 minus, and then I put a negative 5 in there. I'm going to get positive 125 over 10. And then I'm going to get a minus 37.5. So this becomes negative 12.5 plus 37.5 minus 12.5 plus 37.5. So that's going to give me minus 25 plus 75. And oddly enough, this is going to be 50 centimeters cubed, leading to an interesting question about whether or not somebody with a calculus background actually figured out how to do this. Right, to figure out the volume of this. It's 50 centimeters cubed inside there, which is an oddly precise number for a parabola plastic thing they made in a shop. Right? Okay, so So, approach. What's our approach? Our approach is going to be, okay, our approach is always going to be, okay, find the area. Okay. Actually, you know what? Let's back up. We'll give you the advanced course right now. Our approach is going to be figure out which way I'm going to walk. Okay. Now, which way am I walking through the shape? Imagine I'm walking through the shape. I got to find my highlighter. There it is. Okay. Which way am I walking through my shape? If that's dx, I know I want my equation in terms of x. If it's dy, I want it in terms of y. Okay. If once I've done that, I'm going to find my area of my shapes. Hopefully be a shape we can deal with, like a rectangle, a triangle, a semicircle, something like that. We find the area of it. Okay. We find the area of it. When we find the area of it, we can easily do the problem from there. We just integrate as we walk along in that direction. Okay. Now, you're like, okay, how useful is this? Well, it's useful for lots of shapes. I mean, take a look. Here's a jar. Okay, here's a jar. Okay. If I don't count the lid, you can look at smooth across the top here, right? Smooth across the top here. So, if I wanted to figure out the volume of this thing, or how much water would go, it's not counting the lid, well, it's circles I'm walking through, right? I'm walking through circles as I go through this thing. And the circles are changing size, right? So I find the area of the circle in terms of walking this way. So I walk through my circles, okay? I walk through the middle of my circles, find out what the area of those circles would be, and then I integrate from start to finish, okay? And I'd have the volume of this shape, okay? All right, obviously we're going to practice this. Obviously we're going to do several problems together. But this was just kind of about how you do the problems, what's the idea, and what's the approach. Okay? All right. Catch you on. Go ahead and look at the next problem on the back of the worksheet we were working on a moment ago, and then I'm going to work through it with you. Okay?